Okay, so now let's move on to our second model. As we mentioned in the first video, the news vendor model will be to discuss a periodic review system with stochastic demand. So somewhere we will need to use probability to characterize those random demands. So somehow the topics in this video will be slightly harder, but I hope you will just try your best. Okay. So sometimes we sell perishable products. Perishable means there is a selling season, and after it, the value will become almost zero for that product. Some examples are here. One typical example is newspaper. Newspaper at the morning are valuable, but after each day, it will become valueless, almost valueless, right? Or high-tech products. A cell phone in this generation can be sold at a high price, but after the next generation comes out, the current generation product will become valueless. Okay, that's some situation. Or fashion goods. Once the fashion period is finished, then those fashion goods will become valueless. Here, valueless generally means the price of that product will become very low compared with the price that is still in the selling season. Okay, so there are some examples that the products cannot be sold forever. So for example, Coke. Coke is not a perishable product because if you do not sell a Coke today, a glass of Coke today, then you can still sell it tomorrow. That's something that is possible. Or for example, house. House is generally not perishable products or land. They are durable goods instead of perishable products. So for perishable products, sometimes the seller only have one chance for replenishment. For example, if we are selling newspaper, then it's quite possible that we need to determine the supply quantity of each day at the morning or one day before. Okay, we are not allowed to get more newspaper during each day. So in that case, we have only one chance for replenishment. So there is only one time point for we to make orders. That's why we say this is one chance for replenishment. So very often, sellers of perishable products will face uncertain demands, and then the problem will be how many products we should prepare for the selling season. If we are selling newspaper, we ask how many newspapers should we provide at the morning of each day. Or if we are selling, for example, if you are running a store of Starbucks, you need to determine how many breads or salad for the breakfast meal should be prepared, because after noon you will have valueless those products. Okay, so again, the problem is about not too many and not too few. We want to find a balance, but now we need to worry about uncertain demands. So let's try to model uncertain demands. Of course, we will use D to denote the uncertain demand, where D is a random variable. So random variable, if you have not taken any course in probability or statistics, you will need help from your friends or whatever, or me. But let's assume you have done so. So you know a random variable is a variable whose value is uncertain to us. In that case, we will have a CDF and PDF to describe the random variable. And we have a PDF if the D is continuous. A random variable may be discrete or continuous, right? Let's assume it is continuous and the probability density can be described by small f. Let's see some examples. Suppose small d is uniformly distributed between 0 and 100. That means in each day, the demand is within 0 and 100. Somewhere we don't know. But the probability for each for each realization within 0 and 100 is the same. In that case, we say f of x is 100. What does that mean? Well, suppose here I am drawing our probability density function, small f. Within 0 and 100, we have a probability that is, we have a likelihood for each of the realization, and that is 100. Okay? If imagine that you are rolling a dice, then there are 6 possibilities. Each of them are equally possible. So each of them has the likelihood of 1 over 6. For our example here is the same. Between 0 and 100, each single realization has the same likelihood. So roughly speaking, each of them have a likelihood 1 over 100. And then we want to ask, for each region, what's the probability for that to happen? For example, one thing that we typically care about is, given a number x, what's the probability for the daily demand to be lower than that? And we call it a capital F or a CDF. So let's try to draw CDF. Here, suppose I give you x somewhere here. Then the probability for D to be less than or equal to x will be the area here, right? And then we immediately know that probability is x over 100. So for CDF, it will really be like this. Okay, I'm drawing CDF from 0 to 100. The CDF will be this one. Okay, the slope is 1 over 100. And then given each number x, I can get x over 100 as the probability for the demand to be less than or equal to x. So for this particular example, you can see that the probability for D to be less than or equal to x is exactly an integral from 0 to x. Okay, we have this relationship, and that will be the key for further derivations. But at least you know this is uniform distribution. Okay, another example is, let's talk about normal distribution. Suppose our demand is normally distributed with mean 50 and standard deviation 10. What does that mean? That means, suppose this is our figure for it. I have somewhere 50, and the standard deviation is 10. If I know the demand is normally distributed, then the PDF, the probability density would be something like this. Okay, this is the famous normal curve, or the curve for normal distribution. It will be centered around 50, and with a larger standard deviation, the shape of this curve will become flatter, or something like this. Or if the standard deviation becomes smaller, the curve will become more centered. But anyway, you know, normal distribution just look like this. And then if we want to talk about PDF, well, of course, again, given any x, we are asking what's the probability for D to be less than or equal to x, and then that's the area below the curve, below x. Okay, so roughly speaking, it will be something like this. Suppose here we have 50, then our CDF would look like this. Okay, somehow it will approaches 1 when x is large enough. Okay, so that's the basic, a very brief review about CDF and the PDF. Somehow we are just describing the likelihood of each realization of the random demand. Okay, some other things. Let's call CO and CU as the overage and underage cost. These are the costs for ordering too much or ordering too small. Okay, and somehow these costs are just conceptual terms. They come from other terms, and we collect them into CO and CU so that when you have one unit of shortage, you feel like you are losing CU, or if you have one unit left over, you feel that you are losing CO. So let's see what's the possible components. A sales revenue a sales revenue R decides CO and CU. A purchasing cost decides each of them. There may be a salvage value of your product. Okay, salvage value means after the selling season, each of your leftover can be sold to a recycler or whatever at price V. There may be, on the other hand, a disposal fee. That means for each leftover, you need to pay the recycler a fixed dollar D for them to take away your product. Or sometimes there may be shortage cost. That means when one consumer comes in and he does not get the product, there is a loss of goodwill, and we estimate it as S dollars. If we have all these components, then we can describe CO and CU, or we say we can use CO and CU to include all of them. When you have one unit of overage or one unit of leftover, what's the cost for that? You paid C to get that product, but you did not sell it, so that's bad. C is there. And also you need to pay D to dispose it, so that's also a cost. Fortunately, when you dispose it, there may be a salvage value. Okay, so C plus D minus V is your cost for having one unit of leftover. That means if your ordering was more accurate and you ordered one unit fewer, you can save this amount of money. Okay, so that's overage cost. For underage cost, it's very similar. We are asking, okay, now we have shortage. If we had ordered one unit more, how much we may save? First, for CU, we have this R minus C. What's that? R is the retail price. C is the procurement cost. So the difference is the sales margin. For each unit of shortage, our loss is the lost sales. Okay, if we have ordered one unit more, we may earn R minus C. And also, when we have one unit of shortage, we are paying a cost for small s. So summing these two things together, the underage cost will be the lost sales plus the loss of goodwill. So it's R minus C plus S. For different situations, for different people, these numbers may be different, and sometimes you don't have salvage value, and you only have disposal fee. Sometimes you don't have disposal fee, but you have salvage value. Sometimes you don't have both of them. Sometimes you have shortage cost, sometimes you do not. But always, we may express CO and CU in this way. So now, we will take CO and CU as our parameter, and then try to optimize our order quantity. Here, we will try to minimize the expected total overage and underage cost, because demand are uncertain, so the costs are also uncertain. So all we can do is to minimize the expected cost. That's something we want to do. So let's formulate the problem. Suppose Q is the order quantity, and X is a realization of demand. Now, capital D is random. Let's assume it has been realized to X. Of course, the time sequence is we first decide our order quantity, and then capital D realizes. So we see X, and then we may decide what's the realized overage or underage cost. If our order quantity was greater than small x, the demand, then that means there are something left over, right? There are left over. So those left over will give us overage cost. But if our demand is larger than the inventory, then we have shortage. In that case, those shortage is going to create underage cost. Or if we combine them together, we have this expression. Let's use this plus sign to express a maximum function. So altogether, the cost depends on Q and X, the order quantity, and the realized demand. If Q is greater than X, this term is positive, and then we have overage cost. Or if X is greater than Q, the demand is larger, then the other term is positive. Either we are paying overage cost or we are paying underage cost, right? Because they cannot appear together. So this is a realized cost. So the expected cost would be the expectation of the realizations. Okay, and now of course X will be replaced by capital D because this is a random variable or random function, and we are taking expectation of it. And our task is to find a quantity Q that can solve the NLP here. Now we are looking for Q to minimize C of QD or just this expectation. So now we really need to do some algebra. The cost function is this guy. Always we want to see what's the whether there is a convexity of it. Okay, so we need to somehow simplify this expression. Let's try to do it step by step. Because we say D is continuous, we can express the expectation as an integral for each likelihood. Okay, X is the likelihood, X is the realization. X may be within, oh sorry, there is a typo. This guy should be infinite. Okay, X may be any number from 0 to infinite, and given X, we have this realized cost function, right? And each X will appear or will realize with the likelihood f of X. And then from here to here, we divide the range from 0 to infinite to two ranges, 0 to Q and Q to infinite. In the first case, if X is within 0 and Q, we know the first term is positive and the second term is 0. Or in the second region, if X is 0, if X is greater than Q, then the first term is 0 and the second term is positive. So we move one step further. Here, we take this away, take CO outside, or take CO outside. Take CU outside. We will get something like this. Let's do one more step. Here, let's decompose Q and X. So for the first term, this term comes from here. Okay, we take Q times f of X as one term, and of course Q has nothing to do with X, so Q can be taken away. But for X, X must be left within the integral. That's one thing. Also, for the other term is similar. For the term here, it comes from here and here. And for Q is the other term. Again, Q can be taken to the outside of the integral. The last step is the following. For this particular term here, for this one, we can see that this is exactly the definition of the CDF right? Capital F of Q is asking you what's the probability for D to be smaller than Q, and that's exactly an integral of the PDF. And then the second term remains identical. For the third term, it becomes this one. This is the same. And here, from Q to infinity, we know that's 1 minus f of Q. So we get this. Okay? From here to here, mostly we are using the fact that the integral of small f of x becomes capital F of x. Later, we will try to do a first order derivative of the last expression, and you may expect we will use the Leibniz theorem. Okay, let's do that later. Thank you.